Fountain for Pharmacokinetic. So today I am going to explain some of the fundamentals or basics of pharmacokinetic calculation using a fountain model. During the video, I will ask you some of the questions. I would appreciate you pause the video, think about those questions, do some calculation, and then come back, resume the video and look for the answers. That would be the most effective way you can understand this. So the first question is, how would you calculate the amount of water present in this fountain? Like, do not drain the fountain, do not collect the water. It's just like running water. How can you calculate the amount of water present in this fountain? Pause the video, do some calculation, think over it and let me know. So how do you do it? Either it is fountain or swimming pool, or either it is like a bucket. How do you calculate the amount of water? The simple calculation would be like, let's calculate the height, length and everything. But in this case, it is very difficult to calculate the amount of water in the fountain. So how do we do that? So what do we do is, we add some color dye or a drug molecule to add into the fountain, and then we will calculate the concentration. A very classical example is, concentration is equal to mass, that is amount, divided by the volume. So what I will do is, let's say I have 10% concentration of any drug, any colorful drug or color dye, whatever you can say. So to get 100 milligram, I will need 1 ml, correct? We did this calculation in the class. 10% weight by volume is 100 milligram per ml. So what I will do is, imagine the same thing, we are giving dose to the patient. You are required to remove the bubble, but for now, we'll just move forward. This is equivalent to IV bolus, intravenous bolus injection. So as soon as you give intravenous dosing, if there is IV infusion, we may have a bag, we put it into the system. If you have subcutaneous or intramuscular injection, we inject that with just like COVID vaccine or any other drug which we give it for subcutaneous injection like insulin. Or oral dosing, let's say we have a tablet, we add the tablet into the system, and that's how the drug will slowly release and absorb into the systemic circulation. So with the fountain, now we added the red color drug into it. How do we calculate what is the volume in it? So what we will do is, after, depends on route of administration, after a certain time, it's preferably as soon as possible, we will collect some amount of sample. Let's say I will just collect equivalent to 100 microliter, inject into the machine as you can see on the screen. This is called high performance liquid chromatography, and that's one of the most common equipment we use to calculate the concentration of a drug molecule or metabolites into the blood. Once I take the sample, analyzing a HPLC, you will get a concentration. So now, as you know, I have added 100 milligram into it, and the concentration, let's say it comes down to 1 milligram per ml. Did some calculation in the class, converting concentration term from percentage weight by volume to milligram per ml and so on. So for here, your concentration, what you get from the blood or serum plasma concentration is 1 milligram per ml. The mass or the amount you added is 100 milligram divided by the volume. So if you solve the equation or solve this problem, volume would be 100 ml. Okay? So that is how simple, and that's your next equation. Sorry. So this is nothing but the volume of distribution. Your VD, volume of distribution, is equal to the dose we give it to the patient divided by the initial concentration that we consider C0. So technically, the equations still remain the same. We use the same equation for pharmacokinetic parameter, and it is considered as a VD. Volume of distribution is nothing but the amount you inject or the dose given divided by the initial concentration you get in the plasma. So once you calculate VD, the next question is, we added this dye or a drug into the system. If it is a regular swimming pool or a fountain, how to eliminate this dye or how to make this water clear of this drug? There are two ways we do it. Either to degrade it or metabolize it, just like our liver does the metabolism, or eliminate it. So some drug do metabolize in the liver or eliminate it via kidney or the fecal route, or some drug do eliminate it unchanged. They do not get processed into the liver, they do not get metabolized and filtered via kidney and get eliminated from the body. So there are two parameters I will introduce now. Question is, how will you clean this water? So let's say for fountain, we will add a pump which can process the water and absorb or filter, or by either way eliminate the dye or a drug from the system. And second, two parameters, cleaning rate versus cleaning volume per unit time. So there are two more pharmacokinetic parameter comes into picture, Ke and clearance. What is Ke? So as we know, majority of our drug follows the first order rate kinetic. There are zero order, first order and second order kinetic, right? But in our pharmacokinetic models, we mostly use first order because it is not the constant amount getting metabolized. It is about constant fraction getting metabolized. Simple explanation would be, instead of metabolizing 10 milligram drug every hour, our body process it like 10%, like 10, 90, 81, 72. So based on the concentration, the drug get metabolized in our body. So most of our calculations are based on the, and that's the assumption for the next slide, compartment model. First order kinetic in the process. So Ke has a unit, let's say 0.2 per hour. That means some fraction is getting metabolized every hour. That is Ke. It is technically a speed of, and you can get it from the slope. Clearance on the other side is telling you what volume, how much water is getting cleaned per hour from the system. So like a pump, how fast your drug is getting cleared, that is K, and what is the volume? So let's say 10 liter per hour. If it is a clearance, then you can say 10 liter of body fluid or this fountain fluid is getting cleared of your drug per hour. So that is what the explanation for K and Ke and clearance. And collectively, your clearance is Ke into Vd. So whenever you start calculating some pharmacokinetic parameter, these are the initial parameters that you will be calculating: volume of distribution, clearance, and elimination rate constant. So first of all, for all the problem as we discussed in the class, you will calculate Ke. Ke will tell you the speed. It is something like you're driving to Chicago. Either you're driving by car or a train or aeroplane. The equation would be different for all of them. Bottom line is, at a given concentration, you have to drive 100 miles. You're driving at a speed of 80 miles per hour. So after 4 hours, how many miles you covered? Or to cover 400 miles, how many hours you need? And those all the equations we discussed during the class for IV bolus, for intravenous infusion, as well as with the extravascular, that is oral, subcutaneous, intramuscular. So let's move on to the next slide. Again, fountain model, we added the dye, we calculate the concentration, we calculate the Vd. Then we put a pump to clear the drug. We will calculate how fast drug is getting cleared, and we will also calculate, considering the 100 ml we have, how quickly or per unit time the drug is getting cleared from the system. Now the second part. Assume the top chamber is a heart. Second chamber, I will load some organ into it. Let's make it the human body. So I will put heart here. I'll put different organs. Brain, kidney. Oh, brain fell off, but that's okay. And any other organ, skeletal muscle, skin. So as you can see, lungs, right? So we have a heart here, we have other organs like brain, lung, and then we have a major organ, that is liver here, which metabolizes the drug, and at the end you can see this chamber is the kidney, which filters. Assume we have two kidney. This is by chance I ordered this fountain, it came like this. So, and you can see on the screen that absorption, So since we are doing intravenous administration, there is no absorption phase. But when you give a tablet or give subcutaneous injection or intramuscular injection, the drug will release slowly and get absorbed into the systemic circulation. So then you will be having absorption as well. So the drug from the heart, it goes to the different organ, it goes to the liver, and then it goes to the kidney. Based on the property of a drug, lipophilic, hydrophilic, it depends. And therefore, the calculations are much more complicated than simply calculating from the fountain. And that is why we need compartment model and what is compartment modeling. So when we add this organ, so our drug get distributed. Some drug easily distributed into the brain, some drug do not enter into the brain. Some drug goes and sit in the skeletal muscle, some drug do not go to the skeletal muscle, or they goes in very less concentration. So that depends on the drug property. This is a homogeneous system. We consider this as a one compartment system. There are different methods we calculate, we use to predict, to understand and calculate the pharmacokinetic parameters. Compartment modeling is one of the simplest model and it's one of the most commonly used one. So let's say we added this organ, so your dye or drug will diffuse into this organ. If I repeat the same thing, add let's say 100 milligram, your dye will, this is considered a blood, it will stay in the blood as well as depends on its protein binding, lipophilicity, hydrophilicity, it might go, or not might, definitely it will go into organ to some extent, depends on its property. So now if I again take the sample, let's say if I take the sample again after adding the organ, and if I calculate the concentration right now, let's say I got the concentration, let's use this one, your VD would be same, you gave 100 milligram but the drug got diffused or distributed well into the organs like lung, liver, kidney, spleen, those are the central compartment, or peripheral compartment like brain, skeletal muscle, skin, and we got the concentration of 0.1 milligram per ml. What would be the volume? It will be 1000 ml. Initially it was 100 ml, considering one compartment there are no organs, no distribution, and secondly it will be 1000 ml. And you need to understand, this is 100 ml volume. There is no way this could be 1000 ml, that is 1 liter. However, when you calculate it, it gives you 1000 ml. That means its apparent volume of distribution, because the drug disappeared from the blood and appeared into the different organ. But the only thing we can withdraw and calculate, use for the calculation for VD, is calculation of, like VD is nothing but we consider the concentration of drug in the serum or a plasma, and as a result many times we see much higher volume of distribution than it's actually. Like human, we consider 70 kg healthy human volunteer, the volume of distribution could maximally be around 45 liter considering intracellular and extracellular volume, and let's say maximum it goes to 60-70 liter. But many drugs have volume of distribution like 100 liters or as high as 12,000 liters, correct? So that means the drug is not present in the blood, it is somewhere distributed into the organ, and that all depends on the property. So therefore we use compartment modeling. We assume, or this is like hypothetical, body is not actually a one or two compartment, but we assume the body is distributed into one compartment, that when you give a drug, it rapidly distributes through the central compartment, which the organs are highly perfused, or it is two compartment model when it's slowly equilibrate between the peripheral organs. So with that, I think I would suggest, I noted down some of the drug here: metformin, warfarin, cetuximab, there is monoclonal antibody, buprenorphine. Even the drug has a different doses from a different route of administration, the volume of distribution changed drastically. Azithromycin, vancomycin, TFC. So with every drug, there is a different volume of distribution, there are different plasma protein binding, and they all connected to the half-life. How frequently we have to give the drug, or what is the half-life of a drug molecule in that. So just find those values and you will understand 0% protein binding to 99% protein binding and everything, how it really affects its volume of distribution as well as its half-life. With that, I'll stop here for the basic understanding. So usually we follow, it's one compartment is very easy to calculate. When you have two compartments, you have absorption phase, elimination phase, distribution phase, post-distribution phase, that all calculation we did in the class. To make this session little engaging, I propose some sort of poem. Today we learned some kinetic. I agree, those equations are gigantic. But once you plot a simple graph, further calculation would be sliding using graph. Identify the route, order and compartment. Think over equation before final judgment. Learn the sequence for pk calculation. First find k, then t half, c0, vd and clearance. Extravasculars are little complicated, but trust me, your fear is little overrated. Absorption, elimination, there are two slopes. Make sure the kinetic is not flip-flop. Loading, maintenance and dose adjustment. Calculate it for the better patient treatment. Thank you for the listening. Kinetic is interesting. I am not here to be YouTuber. I am very happy being a professor.